Hello everyone, welcome to lesson 8 of our control theory course. In this video, we are going to tackle something more challenging. We will draw a complete block diagram from the RLC parallel circuit differential equation. This is a second order system, which means we'll need to handle double integrals. Before we begin, let's quickly review our 4-step method. Step 1. Check that input and output are labeled as u and y. Step 2. Eliminate all derivatives by taking integrals. Step 3. Isolate y on one side of the equation. And Step 4. Draw the block diagram following the equation. Here's our RLC differential equation. Notice that we have a second derivative of y, which makes this a second-order system. We also have a first derivative term and a regular y term. On the right side, we have our input u. Let's start with step 1. We need to verify that our equation uses u for input and y for output. Looking at the equation, yes, we already have u as our input and y as our output. So step 1 is complete. Now comes step 2, which is a bit more involved this time. We need to eliminate all derivatives by taking integrals. Since we have a second-order derivative, we'll need to take a double integral. Here's the key concept for second-order systems. To eliminate a second derivative, we need to integrate twice. When we apply a double integral to the second derivative of y, we get just y. The two integrals cancel out the two derivatives. Let me show you term by term. The second derivative term becomes y after double integration. The first derivative term becomes a single integral of y because one derivative and one integral cancel out, leaving one integral, and the regular y term becomes a double integral of y. For the input term on the right side, the same double integral applies, so our input u becomes a double integral of u. Now we have our equation in integral form with no derivatives. Step 3 is to isolate y. We want y equals something on the right side. This is where we rearrange all the terms to get y by itself. Here's a useful tip from the previous lesson. When we have integrals of the same order, we can combine them inside a single integral. This makes the block diagram much easier to draw. Let's start rearranging. I move the integral terms to the right side. First, the single integral term 1 over r times the integral of y. This comes from the first derivative term. Next, the double integral term 1 over L times the double integral of y. I'm keeping track of the signs carefully. These terms had positive signs in the original equation, so they become negative when moved to the other side. Now I combine the input and the single integral term. They're both under a single integral, so I can write integral of u minus 1 over r times y. This is much cleaner. Here's our final equation with y isolated. Y equals 1 over c times the entire expression in brackets. Inside the brackets, we have the integral of u minus 1 over r times y minus 1 over L times the double integral of y. Now for the exciting part, step 4, drawing the block diagram. We start with the basic structure. Input u on the left, output y on the right. Then we fill in what happens in between. I draw the input arrow labeled u and the output arrow labeled y. These are the two endpoints of our block diagram. Everything else connects these 2 points through the equation we derived. Let's trace the first feedback path. We take y, integrate it once, multiply by 1 over L, then integrate again. This gives us the double integral term 1 over L times double integral of y. I draw two integrator blocks in series. The output y goes into the first integrator, giving us integral of y. Then into the second integrator, giving us double integral of y. The 1 over L gain block comes before or after, your choice. Now the second feedback path. We take y, multiply by 1 over r, and this connects to the summing junction along with u. This is the single integral term. 1 over r times y. I draw a gain block with 1 over r. The input is y. The output goes to the summing junction. This represents the term 1 over r times y in our equation. Here's where it gets interesting. We need summing junctions to combine our terms. One junction adds u and subtracts 1 over r times y. Another junction subtracts the double integral term. I draw the circular summing junction. The plus sign for u, minus sign for the 1 over r times y term. The output of this junction goes into an integrator, then another summing junction for the double integral term. After the summing junctions, we multiply by 1 over c. This gives us y. I draw the 1 over c gain block and its output is our final output y. The block diagram is complete. Look at our finished block diagram. We have two feedback paths, one through 1 over r with a single integral and one through 1 over l with a double integral. Both paths use negative feedback. The final multiplication by 1 over c gives us y. Remember, there are multiple ways to draw this diagram. You could place the gain blocks in different positions or arrange the summing junctions differently. As long as the mathematics is correct, the diagram is valid. Let's summarize what we learned. For second-order systems like RLC circuits, we need double integrals. This creates two feedback paths in our block diagram. The four-step method works perfectly for these more complex systems too. That concludes Lesson 8. We've successfully drawn a block diagram from a second-order RLC differential equation. In the next lesson, we'll explore even more advanced topics. Thank you for watching, and I'll see you in the next video. Goodbye!